The Future History of Energy and Transportation. Documenting the paradigm shift from the era of oil and internal combustion to the era of robotics. By Julian Cox. Narrated by the author with the aid of an artificial intelligence. Chapter 13. Materials Level Efficiency Explored. Assuming we had numbers for societal level energy efficiency plus infrastructure energy efficiency including vehicle manufacturing energy efficiency, in watt-hours per mile, without trailing off into attempting to calculate the energy to power the private lives of the staff of each industry, that would be a wrap as far as energy inputs per mile were concerned. Of these, the one that matters is societal level energy efficiency, which is the energy to get the energy. The remainder is downstream. There are no additional energy inputs to mechanize transportation from the human economy. In a similar way that the energy costs of operating farm machinery is dwarfed by the calorific output of a corn crop grown in sunlight, nature augments human efforts in the various energy harvesting industries by contributing the stored energy content of naturally occurring hydrocarbons, biomass and fissile materials and the ambient energy usefulness of rivers, geothermal temperature gradients, wind, tides and sunlight. Hence the sum of all energy used in connection with transportation greatly exceeds its societal energy inputs. In the case of fossil fuels, societal energy inputs represent only the fraction of recovered energy resources directed back into mining, refining and delivering fossil fuels. This is 25% in the case of gasoline, that delivers a 4-to-1 return on investment in energy terms, although typically followed by a 25% efficient process in a vehicle, prior to balance of vehicle systems losses, which is why spending 100% of a societal energy resource, electricity, directly on powering a vehicle is now moot or competitive in energy terms. In the case of a solar array, putting aside infrastructure level energy costs, society faces only the opportunity cost of what to do with the fraction of the solar energy intercepted, that is the energy captured and converted to electricity. The concept of a light reserve to underpin debt, as opposed to an oil reserve, was never invented. Electricity is what we get to choose how to spend. Spending sunlight was never an option. Truthfully, the concept of spending a natural oil reserve in the ground is equally absurd, like the table salt industry collateralizing the sea. Perhaps proven solar insolation reserves, pertaining to the net present value of future sunlight falling on a patch of territory, should be considered. Meanwhile, as long as we get our 27 miles out of our 306 watt-hours per mile of electricity, wasting 75% of the sun's energy received on the face of a solar array is immaterial to society in energy terms. Similarly, so long as we get our 27 miles from expending our 306 watt-hours per mile on the fossil fuel industry, the waste of 75% of the energy content of a naturally occurring hydrocarbon in an engine is moot. At least in energy terms. In synopsis, there is a well-founded evolutionary trend towards renewables in energy generation, following the cost curve. Not the numbers required for a revolutionary step change, to break the bank of the fossil fuel economy, so to speak. Not in energy terms alone. Rest assured, market disruption will come, but it will come from the opposite direction. What is more significant to society than energy efficiency, is the disparity in the need to move materials, when compared with transmitting electrical energy along wires, and the opportunity cost of burning vast quantities of materials to power vehicles, as opposed to having access to those materials at the same time as storing and retrieving electrical power, without combustion. Next to consider then, is opportunity cost per mile in terms of the use of materials in transportation, materials level efficiency. To make any sense of this, once again we are going to need to take a fresh look from first principles, to identify the functional equivalence of the role of materials across vehicle technologies. Clearing up a point of energy density. A 100 kilowatt-hour electrical charge, according to Einstein's E equals mc squared, adds 0.000000000000004 006 kilograms of relativistic mass to the battery of a Tesla Model S. The same is expended upon traveling 405 miles. This is the direct equivalent of pumping 8.43 kilograms of gasoline into a gasoline tank for 100 kilowatt-hours of thermal energy input, about 3 US gallons. While it is relatively straightforward to measure the difference in mass between a full and empty container of gasoline, there is also a difference in mass between a full and empty battery. Indeed, if it were possible without missing a molecule, to collect and weigh every ton of the exhaust gases of a vehicle down to the resolution of a small fraction of a gram, there would be a tiny bit less mass than the fuel and oxygen that was burned, due to the lowered energy state of the exhaust products. The difference is significant in energy terms, at least on a human scale, and almost but not quite non-existent in terms of mass. Comparing the energy density of gasoline to the energy density of batteries, whose gross mass is not consumed while driving, is a near ubiquitous error of assumption and the root cause of much confusion when it comes to thinking about cars. The 100 kWh battery accrues only the aforementioned fraction of a kilogram upon filling it up from empty, making energy, without a carrier such as gasoline, electrons if one wants to visualize it that way, 24,962,556 gigawatt-hours per kilogram. When comparing to 12,200 watt-hours per kilogram for gasoline, an electrical charge in a battery is 2,046,111,161,127 times more energy dense. This is to drive the point home that we are not burning fuel in a battery. In terms of relativistic mass of gasoline attributable to its thermal energy potential in air, the bit we are interested in to drive a car is 0.000000014,823 kilograms per 30.3 metric tons. This is the minuscule useful fraction of the 30.3 metric tons of gasoline added to a 27 miles per gallon car at the pump over 300,000 miles in service. The great bulk of the mass, for all practical considerations all 30.3 metric tons of it, simply addresses the fact that gasoline is not rechargeable. Instead, its whole value is in giving us something to work with, such that energetic materials can be brought to the car and exhausted usefully via an engine, proportionately to the application of the gas pedal. An electric vehicle with a rechargeable battery is not able to make full use of the thermal energy potential of its battery constituents to drive the wheels. Rather than burning all of the battery constituents in air, the battery operates within a band of energy states in which the chemical reaction is highly reversible. Preserving the ability to recharge the installed battery chemistry with no materials exhausted or replaced prior to end-of-life recycling, allows the vehicle to deal in pure energy, electricity, supplied at light speed along wires without any energy carrier substrate. Elucidating the functional equivalences of fuel tanks, battery cells, engines, and motors. The concept of a tank of fuel is vital to understand because, as touched upon above, it is subject to a near universal misconception when seeking to compare fuel with batteries. This comes back to a near universal misconception, that the energy density of gasoline, which is approximately 33 kilowatt-hours per US gallon or 12,200 watt-hours per kilogram, relates for purpose of comparison to the energy density of commercially available traction batteries, containing cells of somewhere in the region of 300 watt-hours per kilogram. However, despite the natural temptation to see both a battery and a fuel tank in a vehicle as an energy storage device, this entire concept of comparing energy densities in this manner is flawed, not just because a battery is fueled with electrons instead of an energy carrier like gasoline, but also because there is no functional equivalence between a fuel tank and a battery, either. Despite the brilliance of designers and engineers to optimize fuel tanks for safety and to deliver fuel reliably to an engine, a tank of gasoline remains an otherwise functionless reservoir of consumable fuel. A battery, on the other hand, is an electrochemical machine. This one is worth getting into the weeds for. In relation to a battery, a hydrocarbon fuel is precisely described as a fully reduced anode material, like half of the chemicals in a fully charged battery. In this light, oxygen from the air would be the cathode. In relation to a car with an engine, a fully charged battery cell is precisely equivalent to an engine cylinder, containing a fuel oxidizer charged with one extremely long stroke piston and a voltaic piston rod. The battery cell thus contains the functional equivalent of a single charge of fuel-air mixture within the cylinder of an engine, after the spark plug or similar has ignited it. Unlike gasoline vapor in air, the charged state reactants within batteries do not require a spark or other source of activation energy to commence reacting with one another, but instead they are prevented from reacting spontaneously by the separation of ion and electron pathways, where the familiar electron pathway of a battery, often marked plus and minus, is presented to the exterior of the cell where it can be routed via a useful electrical circuit. The chemical reaction in a partly or fully charged battery cell is at all times exerting the electrical equivalent of pressure on a piston head, similar to a compressed spring. For a battery cell, this pressure is held in place by the extremely high electrical resistance of air between the terminals. Thus, like a compressed spring released from a latch, this force is ready to be released as soon as an electrically conductive pathway is provided between the terminals, for example via an inverter in an electric motor. The battery supplies the function of a moving piston and the electric motor is performing the function of a crankshaft. The electric motor is not a complete engine, because it is the battery that is providing the function of cylinders and pistons. In this way, a Tesla Model S could be viewed as having a 7,000-cylinder one-stroke engine. There is no fuel tank or fuel tank equivalent aboard the Model S, precisely because it does not consume fuel. The single factory-loaded chemical charge in the cells is restored by recharging, including by regenerative deceleration, until end-of-life recycling. It is never combusted and expelled as exhaust, unless in the event of a catastrophic failure. For this reason, an EV does not require an elaborate exhaust system for handling continual thermal runaway events, which is precisely what powers an internal combustion engine vehicle. An EV just requires a means of venting a single thermal runaway event, without injuring passengers in case of mishap. By stopping the virtual piston of a battery, disconnecting the electrical circuit, long before the chemical reaction has turned to irreversible ash, and while all of the chemistry in a discharged energy state is still contained in the cylinder, pushing the virtual piston back up the cylinder by means of overwhelming the voltage presented at the terminals, with a higher charge voltage, charging simply recombines the low energy state materials into high energy state materials. This would be the equivalent of converting CO2 and H2O back to gasoline and oxygen ready to go again. While the exhaust products of internal combustion do not readily return to a fuel oxidizer mix under mechanical pressure, the chemistry of a battery does, under electrical pressure. Conversely, when relating an engine to a battery, an appropriate equivalence is a mobile battery manufacturing plant. That is functionally what an engine is. First, a carefully controlled quantity of gasoline anode material is combined with a carefully controlled quantity of air-containing oxygen cathode material. This is typically achieved by a carburetor or a system of air intakes and fuel injectors. This mixture is not immediately reactive in the absence of an ignition source, and thus these can be introduced into the cylinder as a mixture. This cell is then closed by a valve and the cell constituents compacted by the return of the piston to top dead center. In an engine there is no separator material between anode and cathode for positive ions to cross or for an electrical circuit to capture the electrochemistry of this prospective reaction. Instead, as the piston passes top dead center, an ignition spark, or in the case of diesel the action of a hot wire catalyst or simply the heat of compression, causes the mixture to undergo a thermal runaway, functionally indistinguishable from a malfunctioning battery cell. A thermal runaway in a battery cell occurs when the ionic separator, that is non-existent in an engine, has sustained sufficient fault or damage, that it allows the reactants to combine directly and undergo internal combustion. Unwanted combustion in a battery cell opens a cell vent and exhausts the completed and partially completed combustion products into the air. So it goes in the engine cylinder. The intentional thermal runaway of the anode and cathode materials in an engine is triggered, but rather than simply venting the materials directly, the energy of the resulting combustion is captured in the form of pressure exerted on the piston head and in turn a push rod connected to a crankshaft. This effect is useful work to drive the wheels and supplies various power pickups for a cooling fan, pumps and a generator to support ancillary functions. Once the combustion reaction has neared completion, the piston returns to compact the exhaust products, but as these are irrecoverable ash, mainly fully oxidized H2O and CO2, these cannot be restored to a charged state by the mechanical force of the piston into gasoline and oxygen. Instead, the precise equivalent of the cell vent, the exhaust port valve, opens and the combustion products, along with the products of side reactions and partially combusted reactants, are exhausted. In the case of an engine, very often partially combusted reactants such as carbon monoxide are given an opportunity to complete combustion in a catalytic converter, and some of the mechanical energy of the reaction in the form of sound is baffled in a silencer before finally the whole lot is exhausted into the air. Hence the battery-making machine, the engine, on board the vehicle continually builds more cells and moments later causes them to experience a thermal runaway, captures some of the mechanical energy of the resulting explosion, then expels the spent cell contents via the exhaust system. Unlike the cell case of a battery, engines cannot be made out of thin metal extrusions or foils because the cell casing is required to endure not one thermal runaway as a worst-case scenario, but 54 billion over a lifetime of normal operation, if calculated as 300,000 miles at 40 miles per hour and 2,000 revolutions per minute. Naturally, there is nothing useful left of these 216 billion little single-use battery cells produced by a typical four-cylinder engine, besides what remains of the engine. Like most factories, the lifetime sum of the materials and engine processes generally exceeds the weight of the factory. In this case, just the anode material processed, gasoline, is typically 20 times the weight of the whole car at the end of its serviceable life. The key point is that lithium-ion cells made on the ground for use in cars can manage more than one cycle. A single cycle of a single cell will carry the car, for example, 9,311 centimeters, 405 miles divided by 7,000 cells, and do this for well over 1,000 cycles, as opposed to 53.6 centimeters, only once, in the case of a single combustion stroke of a four-stroke engine in a four-cylinder car, based on 40 miles per hour at 2,000 revolutions per minute. Gasoline therefore is correctly defined, not as an energy product but as the precise equivalent of a refined battery-making material for a single-use battery. A choice of processed mining product used to store and release energy. Neither batteries nor any of the materials they contain are combusted and vented when driving an electric vehicle, because the same material used to store and release energy installed at delivery is continually reused to store all of the energy required until end-of-life recycling. Not combusted and then expelled irrecoverably after a single use. The point of laboring these equivalencies above all else, is to illustrate the continuum from external combustion, coal-fired steam engines, to internal combustion, gasoline and diesel, to no combustion, rechargeable lithium-ion, given that combustion to charge a battery is optional, certainly not required. The fact is, these technologies are merely a rearrangement of functional equivalencies in a sensible progression to achieve the same goal, transportation, or valuable work from machines more generally, with ever greater sophistication in the direction of lowered cost. In this instance, culminating in a radical reduction in materials cost on account of reusability, rechargeability. So, considering we have already accounted for the societal energy efficiency per mile of presenting an internal combustion vehicle and an electric vehicle with gasoline and electrical energy respectively, around 306 watt-hours per mile by either pathway, we can now proceed to make sense of societal resource allocation of materials, net of recycling, to their proper function within the sphere of energy and transportation, storing and releasing energy on board a vehicle during a useful lifetime of delivering value, for sake of example 300,000 miles. For a 27 miles per gallon vehicle such as the 1,582 kg BMW 328i. Curb weight, 100% available for recycling at end of life, equals 1,582 kg. 300,000 miles at 3.7 US gallons per 100 miles, US EPA, equals 30,333 kilograms consumed. Percentage of processed mine materials, by mass, available for recycling at end of life, 4.96%. Materials efficiency, 10.111 kilograms of materials consumed per 100 miles. For an electric vehicle such as the 2,215 kilogram Tesla Model S. Curb weight, 100% available for recycling at end of life, equals 2,215 kilograms. 300,000 miles using a 544 kilogram battery, subset of curb weight, equals 0 kilograms consumed. Percentage of materials, by mass, available for recycling at end of life, 100%. Materials efficiency, circa infinity, net of tires, screen wash and wiper blades. Without trailing off into tires and oil changes, materials that are often recycled, this concludes a fair comparison of materials consumed and hence to a great extent the comparative economic impact and opportunity costs involved in delivering mileage by successive vehicle technologies. However, in many if not most cases, the traditional approach of arbitrarily allocating grid emissions and hence materials consumption to the EV will not be assuaged. Note: as discussed in the head chapter of A Hierarchy of Efficiency, It is inappropriate to apportion the emissions of legacy grid technology, as if it were a property of new electric vehicle technology. Again, if there is any causal link at all between the addition of an EV to the grid and the choices made in the grid mix, it is evidenced in the fact that most of the major players engaged in battery production for electric vehicles, Tesla, Panasonic, LG, Samsung, BYD and others, are also actively engaged in the industrial-scale production of solar energy. In the case of Tesla alone, Tesla Solar's own renewable energy contribution to the grid far outweighs the demands on the grid from its own electric vehicle fleet, with sufficient excess to offset likely most if not all of its factory operations. Globally and in the US, new renewable generation capacity far exceeds and far outpaces new demands from new electric vehicles, and this trend will never change, at any scale, forever. The physics and economics of this statement is inviolable. To put some numbers on that. In 2020, 260 gigawatts of new renewables capacity was added to the grid, globally, up more than 50% from the previous year. With a capacity factor of 24.5% to 34.8% to exclude low light and windless conditions, and applying just the minimum figure of 24.5% to the 8,760 hours in a year, this comes to 558,000 gigawatt-hours of ongoing annual electricity production, or 558 terawatt-hours just to change the units. This is in addition to at least 250 terawatt-hours of installed annual capacity added in the previous year, and 2021 is on track to exceed 1,000 terawatt-hours added. Meaning that new renewables capacity added in a single year, 2021, is set to match the International Energy Agency's, albeit highly questionable underestimate of global electric fleet demands, of 1,000 terawatt-hours in 2030 from electric bicycles to Class 8 trucks and everything between, 9 years in advance. Note: the International Energy Agency, a policy think tank representing a consortium of oil-fired governments and whose policies seek to finesse the global distribution of carbon emissions in negotiation with oil, gas and coal financiers, will assuredly not be responsible for driving the pace of the economic cascade documented herein, that is set to critically disrupt oil-fired governments and fossil fuel financiers, commencing with market disruption of manually operated internal combustion as a technology, long before 2030. Nevertheless, if we must add in the well-to-tank materials costs of supplying vehicles, both electric and gasoline, let's start with the gasoline vehicle. For the 27 miles per gallon gasoline car, we arrived at 306 watt-hours per mile to deliver fuel from the ground to the tank, by back-calculating standard US DOE published figures for well-to-tank CO2 emissions of 2.33 kg CO2e per gallon. Above we calculated that a 27 miles per gallon gasoline vehicle was consuming 10.11 kilograms of gasoline per 100 miles, without calculating any materials costs of supplying the vehicle with gasoline well-to-tank. Again, let's take the DOE 2.33 kg CO2e well-to-tank emissions, and apply it to octane, a somewhat reasonable approximation to an average fossil fuel when the average is diluted by methane, using the following: 2C8H18 plus 25O2 equals 16CO2 plus 18H2O. Molar mass equation: 228 plus 800 equals 704 plus 324. Thus we get 0.7546 kilograms of octane average fuel consumed well to tank, per US gallon delivered to the tank. Over 300,000 miles, divided by 27 miles per gallon times this 0.7546 kilograms, we get 8.384 metric tons of gasoline, to add to the 30.333 metric tons consumed by the vehicle, totaling 38.717 metric tons of fuel consumed for 300,000 mile lifetime. Alternatively stated, there is another 2.79 kilograms to add to the 10.11 kilograms per 100 miles. Totaling 12.90 kilograms of materials consumed, per 100 miles for the 27 miles per gallon gasoline vehicle. Now we have a figure for a US average new vehicle, that we can compare to the total materials consumption of an EV supplied from the current US grid. For an electric vehicle such as the Tesla Model S operating at 280 watt-hours per mile, we can just look up a grid emissions intensity number. For example, 0.610 kg CO2 per kilowatt hour. This is the figure the IPCC cites for the US grid average, as at 2003. According to the EIA, the U.S. grid as at 2015 was split 33% coal, 33% natural gas, 1% petroleum, which by eye, looks a lot like octane on average, as a molecule between natural gas and coal. The remainder, such as hydro, nuclear, wind and solar, is non-net emissions generative. To a good approximation, over 300,000 miles times 0.28 kilowatt-hours per mile times 0.610 kilograms CO2 per kilowatt-hour, times 228 to 704, which is the octane to CO2 mass ratio, we get 16.594 metric tons of octane average molecular weight of fuel, which is a fair estimate of total materials consumed by the U.S. grid to supply a 280 watt-hour per mile electric vehicle over 300,000 miles, or 55.3 grams of grid utility fuel per mile. This comes to 5.53 kilograms per 100 miles to add to the 0.00 metric tons for the Tesla Model S. Hence, to summarize the comparison for total materials efficiency in the U.S. BMW 328i, 12.90 kilograms of materials consumed per 100 miles. Tesla Model S, 5.53 kilograms of materials consumed per 100 miles, assuming the supply of electricity is the 2015 U.S. grid average. Again, net drain on legacy U.S. grid utilities is not true of newly introduced electric vehicles, now or ever. For example, 30 to 40% of Tesla owners at the time of writing are also solar electricity producers. U.S. Tesla ownership is currently concentrated in California, where PG&E claims 0.524 pounds per kilowatt-hour, which equals 0.238 kilograms CO2 per kilowatt-hour emissions intensity, which is less than half the 0.610 kilograms CO2 U.S. grid average. Electricity drawn from the Tesla supercharger network, fast DC chargers, is supplied from whichever source Tesla arranges. Selectively in the future grid corresponding to societal scale EV adoption is not the 2015 U.S. grid cited today by the IPCC or the PG&E figure. It's the grid that exists in the same future. Supply-side emissions are not inherent to electric vehicle technology and do not scale society-wide, when in point of fact incremental new electric vehicles and incremental new renewable generation are added to the grid simultaneously, and renewables are added by the terawatt-hour annually, at a far greater rate. In Norway, the IPCC grid emissions intensity number for the Norwegian 98% hydroelectric grid as at 2003 was 0.003 kg CO2 per kilowatt-hour, compared with the 0.610 kg CO2 per kilowatt-hour in the US. This alone reduces the 16.594 metric tons of power generation fuel materials consumption per 300,000 miles we just calculated for the Tesla Model S, using US grid average electricity, to 0.081 metric tons in Norway over 300,000 miles, without any alteration to the vehicle. A 99.51% improvement in materials efficiency. Like for like, in Norway this 81 kilograms per 300,000 miles is a 99.75% improvement over consuming 38.717 metric tons of non-recyclable materials well-to-wheel in a 27 miles per gallon BMW 328i over 300,000 miles, in Norway. Economic implications of the society-wide opportunity for efficiency gains like this in the use of materials to deliver passenger miles, ought to be obvious. At scale, materials efficiency gains, more so than energy efficiency gains, will prove determinative. This is not just a matter of tremendous cost savings on the necessity to first move and process gigatons of materials to enable cars to move. Norway, a petrostate, case in point, is moving its domestic vehicle fleet aggressively to electrification powered by renewable energy, principally hydroelectricity, with the elimination of drastic import tariffs levied on vehicles, in the case of electric vehicles, plus additional incentives such as toll-free ferries, in order to have its cake and eat it. Norway by this policy is freeing up its domestic oil production to maximize export revenues. Naturally, the principal market for Norway's oil at the time of writing is combustion fuels. Nevertheless, it illustrates the point that renewable-powered electrification, asset-based rather than combustion-based power, has freed up valuable materials for Norway to sell, instead of burning them. In summary, there is both cost and opportunity cost, to come up with an extra net 38.617 tons of processed mine materials, fuel, for no reason that can be explained as a benefit to the paying customer, when in terms of extra passenger miles and luggage transported on top of the 81 kilogram option, there is no such benefit. The entire difference comes down to the ability to cycle the energy carrier in the battery, as opposed to choosing an energy carrier material that must be exhausted after a single use. Secondarily, the ability to supply an essentially massless fuel in the form of electrons, harvested from photons or another ambient capture device like a hydroelectric dam and delivered to market at light speed along wires. The opportunity cost to society of burning gigatons of organic chemistry, suitable for an endless list of everything from clothes, housing and medicine to advanced composites such as wind farm blades, cars and aircraft, even synthetic graphite and electrolytes for batteries themselves and the superstructure if not the chemistry for photon capture, is simply an egregious economic waste, quite besides any consideration economic or otherwise pertaining to emissions.